Hi everyone, I'd like to do a problem solving video where I'm going to solve this problem. I have two masses, two books, and of mass M1 and mass M2, and I'm going to push on the upper book with a force F. The problem states that there's almost no friction on the table, but there is a friction, a coefficient of static friction between the two here so that the book can move together. Okay. The question is, with what maximum force can the upper book be pushed horizontally so that the books move together without slipping? So what is the maximum F before these books stay together? Alright, I have this problem solving worksheet where I have all the steps outlined for problem solving, so I'm going to use that. The first step is to model. Model just means like what are the assumptions we're making when we solve this, and essentially it's stated in the problem. It tells us that the friction is almost zero on the table. There's one assumption. That's pretty much the only thing we really need to write here for modeling. We're going to use the particle model, of course, but that's not particularly important to write since we do that almost always. Okay, we are in the problem. We're given M1, we're given M2, in the sense that they're stated to be potentially known value, and we're given the coefficient of mu s, and they're asking us to find the maximum force, F max, presumably in terms of these three quantities. Alright, let's get started. I don't know why they would be a F max, so first, probably the best way to start when you visualize, draw a free body diagram. I can draw a free body diagram for M1, for M2, or for both of them together. I don't know exactly what I'm going to need. For sure, I'm going to need M1 because I'm going to need F. So I would start with M1 and M2, and then if we need both of them combined, we can always draw that diagram later. So, alright, let's draw a free diagram for M1. So what force do I have? I have F. I'm going to have gravity. I'm going to have a normal force. And the normal force is, let me be careful, it's 2 on 1. And then what else? Well, there should be a static friction between the two, and presumably it's this way. So this is Fs, and again it's 2 on 1. And that should be it. Let's look at M2. So M2 has gravity. Has a normal force from the table on 2. This capital F force is not acting on 2, so it should not appear here. But there is a contact between 1 and 2. And such a contact will lead to a normal and a friction. And essentially they should be the third law partner of these guys. So there should be a normal downward, so 1 pushes back on 2. So this is 1 on 2. And there should be a friction to the right. Friction 1 on 2. This force here and this force are third law partners. And 2 on 1 and 1 on 2. And this force and that force are third law partners. It makes sense that there's a static friction to the right. This is what's going to make the book 2, M2, move to the right. So the reason they're going to move together, to the right because I'm pushing M1 with a force F, but also what's pushing F2, M2, is really the static friction from M1. And I guess the idea is there would be a maximum F because I know there's a maximum static friction. So as I push harder, this thing should accelerate more, and so this is going to have to be bigger. But there's a maximum value it can be, and so there should be a maximum value for this. So in order to find the maximum value of capital F, I just need to solve for capital F, assuming that the static friction is maximum. Okay, so let's get started. So to solve, we use Newton's second law, sum of the forces equal ma. We're going to do this for M1 first. Let me put a coordinate system. This is x, this is y. So M1 in x direction, I just have F minus Fs 2 on 1, and that should be M1 times AX, and then be 1. So this is the acceleration in the x direction of block 1. And then in the y direction, I have a normal n2 on 1 minus fg, which is just going to be m1 times g. And that should be equal to 0, because there's no acceleration in the y direction. Okay, so that's block 1. What about block 2? In the x direction, there's only one force. So it's just Fs1 on 2, and that should be equal to m2 times ax of object 2. And in the y direction, there's 3 forces, and I doubt we're not going to need this nt on 2. This sounds dubious, so I'm not going to write this. Skip for the moment. Can always come back if I need it. It sounds like it's not going to be a useful equation. So all right. Okay. So, well, first thing, I have I've been very explicit. I wrote 2 different accelerations, but if there's no slipping, then they should move together. So that means that ax of block 1 should be equal to ax of block 2, and I'm just going to call it ax. This is the acceleration constraint. I'm being very explicit. Most people would have done this without even thinking, but in cases, they could be different accelerations, or they could be minus sign different sometimes. In this case, they're just moving together as one, and so they must have the same acceleration. Technically, it's an extra thing we need to do to solve the problem. So acceleration constraint. Then the other thing is we are going to want to solve capital F when the static friction is maximum. So what is the maximum static friction? Well, we know from modeling that should be just mu s times the normal. I need to use a normal that's relevant to the static friction, so I need to use n2 on 1. The normal force, I can just see from this equation, is just going to be equal to m1 times g. So this is just mu s m1 times g. Great. And by Newton's third law, this is also the same as Fs1 on 2. So this one and this one should be equal. Okay, so then I can just plug that into, let's call this equation 1. Let's just put this into 1, so it's going to be F minus the static friction, which is mu s m1 times g. That should be equal to m1 times ax. So I'm close, but I still don't know what ax is. Oh, but look. Yeah, I can solve for ax in terms of static friction just from this. Let's call this equation number 2. So from 2, I found that ax should be equal to the static friction, this one, which is mu s m1g divided by m2. Okay, so I can put that back in here, and then I get F minus mu s m1g equal m1 times mu s m1g over m2. All right, let me put this on this side and kind of message it. But as you can see now, I have just something just f in terms of mu s m1 and m2. So essentially, that must be the answer. So f must be equal. I'm going to put this on this side, and I can probably factorize this factor. So I get mu s m1 times g times just 1 plus m1 over m2. And this must be the answer. It looks right to me. This is a force. In fact, it's just a static friction force times a factor 1 plus m1 over m2, which has no dimension. So that's good. And if m1 was 0, it would just be F would be equal to the static friction. Kind of makes sense. So I'm not going to spend too much time on the assessing part in order to keep the video short. But the idea is then you can go and check whether your answer makes sense. To me, this looks good at the moment. Okay, thank you.